Hello, students. Chapter 6 with 6 and 7 to go. That's all there is. So we're going to take a look at chapter 6. This is rational numbers. I'm again in class. I mentioned that rational starts with ratio. And so these are numbers that can be put into a ratio. And so we'll see that we'll start with what are the numbers. So the set of rational numbers, how do we describe them? How do we tell about an order, like which number is larger than another? Then we get into addition and subtraction, multiplication and division, and then the last piece is proportional reasoning. And this is something that is used across nearly all grade levels. It's mostly integrated into an integrated math class. So proportional reasoning is not something that's just kind of a one topic. Okay, let's see here. We're going to jump to the next page. All right. So we do start with the idea of why do we have these? Where did they come from? And what's interesting is across all of mathematics, we tend to create things that are needed, but only when we need them. So in the past, we might have had something like what number plus 2 is equal to 3. And we would try to find that number. And that number turned out to be a natural number. And so we use natural numbers as long as we can until sometimes we get to what plus 2 gets you back to 2. And all of a sudden, natural numbers fail. There is no natural number I can use. So then we say, okay, we started with the set of natural numbers. And then we say, you know what? I need another symbol here. I need something I can add to 2 to get back to 2. And that's where we added in or adjoined a new number. And we created a new set. So we started with the natural numbers. Then we got the whole numbers. Okay. Then we had, well, what if I add 2 and I get to the number 1? Well, now that's not a whole number, right? Because when you think about it, it's what we just got through in chapter 5. I have to add something that takes me backwards. So that's where we come up with the integers. Now, the integers, depending on the textbook, you may see some books use I for integers. Again, those are the whole numbers and their opposites. -1, -2, all the way down. But you also might see some books use Z, and sometimes Z that looks a little fancy to be the same exact thing. So it totally depends on your textbook as you go forward. Both of these are just fine. Usually, I think I try to reserve I for the kind of irrational numbers, but we'll worry about that when it comes. Okay, so these were all with addition. Then we had some other things like what if we solved multiplication, right? So 3 times x is equal to 3. Again, that was a natural number. 3 times x equals 0. That would have to include a whole number because 3 times 0 would get me 0. 3 times something that got me to -3. Now we got to bring in the integers. And then we're going to come up and say, well, what if I had 3 times a number and it equals 5? Well, there's no natural number that makes that happen. There's no whole number. There's no integer. And when we try to figure out, is this the case? Even back in chapter 4, we would have said 3 does not divide 5 because there is no multiple of 3 that gets you to 5. And so there is no whole number. There is no integer. So we need to create a new object. And that object we're going to say is this object, this thing, is what I would multiply by 3 to get to 5. And so that we tend to write this way. And so this is our first idea that if we chose the number 1, 1 times 3 would get me 3, 2 times 3 would get me 6. I cannot use the whole part of 1. I cannot use the whole part of 2. I have to take part of those. I have to break one of the whole numbers up, and that gives us a fracture or a broken piece, which leads us to the word fraction as a number. So we have to have a new set of numbers so that we can do different things. These would include numbers that are not an entire whole number. So this is going to be the set of rational numbers. And as defined, here's the idea. Rational numbers, think about the ratio. A rational number must be written as A over B. A over B are integers, and B cannot be 0. Okay. Yes, the top part is the numerator. And if you think about it, the numerator is the name. Okay, so numerator comes from the word name, and denominator comes from like denomination or type. So when you look at a fraction like this, 3/5, what we're really saying is I have 3 of the fifths, just like you might have 3 coats or 3 pairs of shoes. So the 3 tells you how many, that's the name, and the object that you're describing in the denominator tells you what type they are. So as we'll see when we get to section 6.2, addition, when you're adding things together, you have to add like objects. So 2 apples plus 3 apples gets you 5 apples. So if you want to keep with that kind of name, if you go with 2 apples plus 3 oranges, we can't say 5 apples and we can't say 5 oranges. We would have to create a whole new type of word, like 5 pieces of fruit. So again, be careful with this as you're doing fractions. Fractions are the first time, you'll probably be the first time a student sees fractions. And again, we get them as early as grade 3. Okay. So that's interesting. Again, you'll see probably some fractions being developed prior to getting integers. So that means when you're doing fractions, you probably will not have the ability to go into negatives. So just be aware of that. Okay. All right. So A over B. So here's what we got. Where can we see fractions? We see fractions typically in these main parts. Probability, when we're talking about chances, the chances are 1 chance out of 2. A ratio, which tells you how many to how many. And just realize when you do a ratio, when they say 3 to 5, it matches up with the objects that they're describing. So if it says 3, I'll do this one in blue. Oh, wait, I did that wrong. I'll do this one in blue and this one in blue. So you can kind of see the 5 goes with the Democrats, the 3 goes with Republicans. All right. A portion. So someone received half of Mary's salary for alimony. All right. Guess that's okay. Division problem or solution to a multiplication problem. So the solution to a multiplication problem typically involves division. And so the solution to that, if you look at this, kind of saying 2x equals 3, you would divide by 2 on both sides. So 2x divided by 2 is equal to 3 divided by 2. And then the result, 3 divided by 2, would be 3/2. And we'll also see, some of you may already be kind of at the stage where you're like, hey, isn't that 1.5? And the answer is yes, it is 1.5. And we'll kind of get to see why it ties back in to our definition of division. So good stuff coming right here. We've got our definitions down. Again, rational numbers have to be an integer divided by an integer. Okay. All right, so different models. There is a number line model. Number line model is where you take, oops, there we go. We take the length between two numbers, and the denominator tells you how many pieces to cut. So if you had a denominator of 3, you would want 3 chunks cut between your whole numbers. If you're using a set model, you don't have to cut things up, because then we're taking maybe 3 out of the 5 total. The bar model is one I really like. And again, I didn't grow up with those. I grew up with teachers trying to do circles for everything. So like, here's 1/2. Okay, well, that makes sense. It's a circle. Here's 1/4. They'd always use circles. And the issue that you're going to have with circles is how do you draw like 4/7 with circles, right? You can't come down and say there's eights. You can do eights pretty good. So you can do 2s, 4s, and 8s because you're just cutting things in half. But even thirds is not easy, right? You have to be able to split it right down, kind of like make almost like a peace sign, but you need them to be exactly the same size as you do that. It's not easy. So thirds might be the easiest to do. But what I want to show you is if you instead switch to a bar model, watch this. You can then say, let me cut this in half. And you're thinking, oh, that's only for halves. And all you have to do is kind of come at the end and just tack one more on. And now you've got thirds and they're the same size. So it actually can be a little bit quicker to do, especially if you're maybe good at making quarters, you could make fifths very quickly. Okay, so just take any length of a bar and just cut it in half, which we can do pretty quickly. Cut those in half and now you've got fourths, but if you wanted fifths, all you have to do is just draw one more at the end. And you've got fifths. And it's much easier to do than with a circle. So please take a note of that. If you're going to be in the classroom with kids, it's probably easier to use the bars to represent than trying to draw circles. Okay. Let's see here. What else? Fractions. Anytime you do a fraction, there is the idea, because what we're really talking about is there is a whole, like what makes one whole object, and then how many pieces did you break that object up into? That's your denominator. And how many did you select? That's your numerator. Okay. So let's try. So as an example, you could create a shape, right, that looks like this. And you could say, this is my whole object. So this, in a sense, is what you are considering one object. So if someone said, oh, I want to break that into 5 pieces, right? Well, then you'd have to cut this so that there are 5 equal pieces. You cannot do something like this and say, okay, 1, 2, 3, 4, 5, and say, okay, those are fifths. Because when we're really representing it, we want that amount to be equal. This one looks big. And if it's bigger than the others, it represents more of the whole than the other portions do. So you want to be very careful about that. Okay, so as you draw it, you want it to be really clear. And again, it has to be same shape, sometimes same size. And here, as you can kind of see, this one is 4 pieces, 1, 2, 3, and 4, and they are all the same shape and the same size. The next one has a 1, a 2, a 3, and a 4. Those actually have exactly the same size in terms of like area, but they're not the same shape. So what we're saying is that either one of these would be okay because the numbers must be equal sized. Okay. So this one, both of these are okay. You will probably start to see that your students prefer this one because the size and the shape does make it a little bit easier to see. Right? All right, let's get a link back. Big star here. Link back to division with a remainder. So when we had something like 12 divided by 5, we would rewrite this as 12 is equal to 5 times 2 plus 2. So we have this object over here called a remainder. Okay. So the remainder had to be less than or equal to the divisor. So 0 had to be less than or equal to the remainder, and it had to be less than the divisor. So that's what it took to have a remainder. So if someone was trying to divide something and they said, oh, I ended up with 5 times 1 plus 7, we would look at that and say, hey, wait a minute. You can make another group of 5 out of this. Go make another group of 5. That's not a good remainder. And that concept holds true when we get to fractions. So when you write a fraction out, a over b, we say if a is less than b, look, it's the same inequality, right? Then we would say the fraction is proper. Now, what we're really just saying with that is that the value of the fraction is less than 1. Okay, that's all we're saying, less than 1. Anything that is not meeting that definition, which means that if you write a fraction and a turns out to be greater than or equal to b, and b is also greater than 0. I'm going to put that in there because, again, b could have been, we said integer, so it could have been a negative number. So if it's negative, we'll just simplify it. But if a is greater than b is equal to 0, then we have an improper. And it's not that it's bad. Improper, sometimes we think, oh, that's bad. It's not bad. It just means it's larger than 1. Okay, so back in a certain period of time, you had to write all of your fractions as between 0 and 1. Anything above that would have been improper, and you'd have to simplify. And yes, it is possible for you to rewrite this as one whole object, which would be 4/4 plus 3/4. And some of you may even write it this way without the plus sign. Maybe you write it as 1 3/4. Yeah, that's perfectly fine. 3/4 is a proper fraction. 7/4 would be considered improper. All right, let's move on. There is a fun historical note. Fractions, they're not just us. They were actually used a long time ago in Egypt. So they had a fun system where every fraction they wrote had to be a unit fraction. And the unit fraction means it had to have a numerator of 1. So that was that was kind of fun. But everything had to have a numerator of 1 to make it work. All right, so there you go. All right, let's take a look at a few other pieces here. Rational numbers. So we said it has to be an integer divided by an integer. So here's an integer, there's an integer. And what's great is that that is equivalent to 3/1, which is equivalent to 3. So basically, any natural number, any whole number, and any integer can be written as a ratio. Okay, so if you think about the number 5, you could just say, oh, that's 5/1. If you want to keep going, you could say, hey, that's actually 10/2. Hey, that's actually 15/3. And all of those represent the same thing. So really, any number you're thinking of can be written as some multiple kind of on top and bottom. So if you wanted to use 3 up here for 5, you use 3, you'd have 15/3. And this is true as long as k is not 0. And again, k, because we'd just be kind of dividing by 0 then. Okay. So yeah, oh, and someone usually asks, what about 0? Sure, I can write 0 as a fraction. 0/1. I could write it as 0/2. I could write it as 0/3. I mean, all of those work just fine. There's nothing wrong with that. Let's see here. Let's move on. Rational numbers on a number line. So grade 3 Common Core. If you take a number line, then what you want to do is be able to mark off something like 2/5. They want you as the teacher to be able to say, okay, here's a number line. Mark where 0 is, mark where 1 is, and then say, what do I want to make? I want to show a student 3/5 on a number line, which means the first thing you have to do is you have to make something that is 1/5. So this is where if you draw your number line like I have here, it's going to be a challenge. So when I draw my number lines, this is going to seem a little strange perhaps, I cheat. And the reason why I cheat here is, watch this. I know that if I can find 5 equal pieces, that it's going to be easier. Remember what I said earlier? It's going to be easier if I break this in half, break these in half, and then I have 4 equal pieces, and I will just make one more equal piece, and then I will draw my number one. So that makes it easier to show each one of these little chunks is 1/5. If the one is already up there, it's hard to make exactly 5 equal-sized pieces. So that's what we're doing. We will see, you can do it. In geometry, we get a chance to do it. We can show how to do it precisely every time, but that'll be in Math 106. Okay, so if you want to count 3/5, remember basically what you're doing is each one of these little tick marks is 1/5 from the previous number. That's lengths of 1 over b. And you could then say on the number line model, I would go over 1, 2, 3 of them, and that mark would be 3 of these fifths. And that is how you can demonstrate where 3/5 is. Same is true for negatives. So again, my tip to you, I hope you take it because I think it's it makes things a whole lot easier to deal with. So if I needed to make sevenths, right? You could just start by making little tick marks if you wanted to. So I might even make a tick mark here and say, okay, well, I can split that in half pretty quickly. I can even split that in half pretty quickly, right? So right now I have 1, 2, 3, 4. Okay, so that's fourths. Well, fourths is not sevenths. So if I wanted to, the other thing you could do is come back and say, well, cut these in half. Watch this. 1, 2, 3, 4, right? So now how many would I have? If you count all of the marks, you have 1, 2, 3, 4, 5, 6, 7, 8. That's 8. That's too many. But all you have to do is come back and say, oh, right here, there's the number 1. And that means there are 7 tick marks to get you there. So that if you wanted to know where 2/7 is, you would just count in 1, 2 tick marks. I chose different color on purpose so that you can kind of see how to make your first marks and how to make your second marks. Okay. If they already, like if they give you a 0 and a 1, just, you got to do your best. I'm not going to lie. You're going to do your best, and it's not easy, right? So if this is right in the middle, that would be like 3.5/7. So this would be like 3/7. Maybe that's 4/7. And then I'm trying my best to make them the same size. 1, 2, 3, 4, 5, 6. I don't know. That one in the middle looks bigger than the other one. So that's not my favorite way to do it. But again, sometimes you may be asked to do that. So again, just do your best. So much quicker when you can control the size, though, when you're kind of in charge. That's nice. Oh, and one more thing about negative numbers, just so that we're kind of all on the same page. Remember, it said an integer, so -3/1. That is exactly the same as -3/1, or the opposite of 3/1, which is actually the same thing as 3/-1. All 3 of these are the same, but what we do, at least in this country, is we kind of say this one over here, we get kind of the frowny face for, okay? And the reason is we want as much as possible for things to be consistent. And it's usually easier if what you're talking about is non-negative, okay? So if you have a denominator that is negative, bring the negative up to the top. Bring it up here. Okay. So if somebody said 5 to -2, you're going to say, okay, that's the same as -5 to 2. And then you can move with your problem. And if you need to, this is the opposite of 5/2. So you could bring that out in front as well if you prefer. But warning, 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 if you had something like -5/2, then you'd have to do this twice, and you'd end up with something like this. You'd have to do it twice. You'd have the opposite of the opposite, which we know turns out to just be that number. So if you do have two negatives, think of it as dividing negatives, and we already know divide by negative makes it positive. Okay, so just a little warning there as we're going forward. And let's continue on. Here we go. How to locate the following numbers. Now notice they gave you denominators of 2 and 4, and that's really helpful because you can break things in half very quickly. And if you break them in half again, you get quarters. So that's kind of the nice piece there. Let's see here. Grade 4, you have to deal with equivalent fractions. And equivalent fractions is actually really cool because if you use that kind of that box model. So I'm going to make a box here. Okay. And then I'm going to show you. So if I cut this box in half, right? So what I really have, if you think about this kind of region over here, that is 1/2. Let's just say 1/2 of a candy bar, right? So I just gave you half of a candy bar. But then the next day I come back with exactly the same candy bar, and this time I cut it this way as well. But I still give you this portion on the side. I give you this whole portion. Well, you can see from this that you still have half of the candy bar, but that half is now 2 pieces. It just happens to be 2 of the 4 pieces that you would have. Okay. And you could continue with this. You could say, well, wait a minute. What if I cut this part in half and this part in half, right? Well, now you have 1, 2, 3, 4 pieces out of the 8 total. But notice in every one of these situations, you have the exact same quantity of candy bar. So 1/2 is the same as 2/4 is the same as 4/8. You're not changing anything. So what we say is that these fractions are equivalent. Even though they don't look the same, we say they are equivalent because they contain the same amount of an object. They would also match up perfectly on a number line. Okay. And here's another illustration. This represents 1/3. So they broke it into 3 pieces. Then they cut each one of those pieces in half to make 2/6. And it's the same quantity, same amount of paper, same amount of candy. And then they did it again, broke those in half. Now they have 12ths, but guess what? 4/12 is the same amount as 1/3, as long as we're talking about the same whole object. And this does come up with, I guess I'll use actual pizzas, but if you had a small pizza and then somebody else had a large pizza and you came over here and you broke this into 4 pieces, right? And you broke this one into 8 pieces, it is possible that one of these pieces, 1/8, could have more pizza in it than one of these pieces, which is 1/4. It is possible, but that does not mean 1/8 is bigger than 1/4, right? We need to be measuring it on the same whole object. So that's an important piece to make sure that we're always using the same whole object. What do we have for this class? In the back of your activity manual, you'll have these things called fraction strips, which are just strips of paper, hard paper, cardboard basically, that are cut and labeled so that you can actually measure things out with fractions. So we have 1/3, one's whole group. We have the thirds, the sixths, the ninths, and the 12th. And so for this, the red object, the long one, is always thought of as like the one whole. But you could create new whole groups by just putting pieces together. So, and we'll see that when we get to division. All right, new theorem. Whoop, whoop. We get theorem 6.1 or 6-1, and that theorem is very clear, and it's really a handy one. It is called the fundamental law of fractions. And so this is something that I do a lot of. I love dropping that F-bomb and flopping. And if you haven't floffed before, I think you're going to enjoy it. Floffing just means that I can take a fraction, any fraction, and I can then create an equivalent fraction, that's the equal sign between them, by multiplying by any number on top and bottom, as long as I don't pick 0. So if you wanted to pick the number 10, just pick 10 for top and bottom, and you have a brand new fraction. It looks different, but has exactly the same value. So you can change the way a fraction looks. It has the same value, but it looks different. What if you didn't choose that? What if you chose 7 instead? All right, put 7 in. 7 times 2 is 14. 7 times 3 is 21. All right. So now this hopefully helps you see why these are all equivalent, but they're a little harder to tell what they are equivalent to, or that these two are actually equivalent without a little bit of work. And that is why we oftentimes refer to something as being in lowest terms, or sometimes people will say it is a simplified fraction. And simplified means that the GCD of numerator and denominator is 1. They have to be relatively prime. So clearly for 20 and 30, they are not relatively prime, right? They have at least a 10 in common, we can see, which means they have a 2 and a 5. So we would simplify by unfloffing. So remember, this equal sign here goes both directions, right? I know it's written in one direction, so most of the time you might look at this and say, okay, that's what makes a fraction look different and bigger. But this is an equal sign. So the opposite is also true. So you can actually simplify fractions with this by floffing. So the fundamental law of fractions, you get to reduce things. So if you had 8/12, you could think of this as 2 times 4 and 3 times 4. And when you see the common number, and it has to be exactly the same, that's the fundamental law of fractions, you could fluff it, fluff, fluff. And you could write at the end a beautiful reduced fraction. Okay, so get used to floff because that's going to be our friend. Some people might say I cancel things out, and technically you are, but really what you're doing is almost like dividing common factors. Okay, so that's probably a better approach to think of it as instead of canceling, because you can cancel things a lot of ways incorrectly. So we're not gonna we're not gonna do that. All right. Simplifying fractions comes the next one, and that's just floffing advanced. So find that GCD if you need to. And really, there is kind of a quick way. If you can find the GCD, you can actually, so for example, if I had this and I was trying to simplify 60 and 210, I could find that GCD, right? 60 is 2 times 3, that's 6 times 2 times 5. 210 is 2 times 5 times 3 times 7. So when I look and see what's common, right, I have 2 times 3 times 5, which is 30. So what I could do is I could think of undoing the 30 for each of them, and that leaves me with 2 over 7. I guarantee at that stage we would have the GCD of 1. So that's kind of a quick approach. Although, again, if you find yourself kind of saying, wait a minute, 60 over 210, Scott, wouldn't I kind of like get rid of a factor of 10 first? Perfect. There's nothing wrong with that. And then you could say each of these has a factor of 3, right? So you'd say, okay, let me get rid of a 3 here. 3 times 2, get rid of a 3 here, 3 times 7. And once the 3's go away, you also end up at 2 7s. That's totally, absolutely. So this is just kind of multiple steps, and depending on how big your numbers are, maybe you want to find that GCD, but maybe not. Regardless, you need to make sure the GCD is 1. Let's move on down the line. So there we go. Yeah, if you do have a calculator for these, you oftentimes can make your calculator turn things into simplest form. I'm trying to think here. The TI calculator will do it. I'm not sure if I have a calculator on my desktop that'll do it. Let me see if I've got a calculator here. Maybe. Let's see here. All right, let me try sharing my screen with this calculator. So this is a Casio calculator, which is perfectly fine to use. Let's see here. So here's the Casio calculator. And so if I did 12 divided by 15, I can press equals on this calculator, and it will give me the fractional component in simplest form. Most of you, your calculator would probably show something like a 0.8 if you do it, because most calculators are set to go into decimal. If you do, and you have like a Texas Instruments calculator, there's usually a button that says F to D, like fraction to decimal. You might have to press shift or second to get into it, but that's the one that'll go back and forth between fraction and decimal form. So totally cool to be able to do that. Let me go back to where we were in the book. So that's a little technology piece that, again, I think is pretty helpful. But if you're new to it, if you're using your cell phone, most cell phones don't have that. I think Desmos does have that. Let's see. Math tools. So for Desmos, there's a 4-function calculator, scientific, and graphing. Let's try the 4-function and say 3 divided by 7. And there it is, and I can see it shows up. So 4-function calculator does not show the fraction portion. Okay, let me try a scientific calculator. Let's see here. So if I did 3, ooh, there's a fraction button there. So ooh, got it. Okay, let me delete fraction button, and I put 3, and then I need to say 7. And there it is. Oh, there it is. So in Desmos, if you see this little icon next to it, it will convert it to a fraction. So that means if you had like 10 divided by 12, it'll write it as a decimal, but if you click this button, it will put it as a fraction in simplest form. So there you go. Okay. And I think, is there the, no, doesn't look like it. I think if I maybe in the graphing calculator, which seems weird, there is a full calculator over here as well. So if you say 10 divided by 12, there is a little button on the side that you can click and it will turn it into the fraction. So it's just right there on the side. Yeah. And I can't remember. I think they do have a GCD built into Desmos now. So the greatest common divisor I can find is 2. And LCM of 10 comma 12 is 60. So I can get that if you're using Desmos. Again, more and more, some of these pieces might be coming to Desmos and coming to classrooms because Desmos is accessible. It's free. You can put it on any device, and a lot of schools have Chromebooks and things like that that work out really nicely. So, okay, let's jump back over. All right, so you may be asked to solve equations, but you can use them with the fundamental law of fractions. Fluff it. Okay. Down here, you're being asked to simplify, which means fluff it. Find a common factor. And some of them you will not be able to because they're not a common factor. And I want to be very clear about this because if there's a problem with students, they tend to have issues with something like this. X plus 3 divided by 3. In many students' minds, they want to do this. They want to cancel the 3's out. The issue is that there is no cancel property. There's only a fundamental law of fractions. And in order to fluff it, it has to be a multiple or factor. And up here on top, There's a 3 right there, but there is no 3 in front of the x, so therefore it is not a factor, sadly, and big sad face with a tear. This is completely incorrect. Do not do this. Okay. If you see something like a 3x plus 6 and the whole thing is over a 3, and your gut tells you to cross the 3's off, at least take a moment from this class, take a breath, and say, I fluffing love fractions. And what you have to do with fractions is you have to fluff them. So that means you have to find a common factor. And up on top, there is a factor of 3, but what remains is x plus 2. If you're wanting to remember, factors come from multiplication. So if you are multiplying, you can do this. When you see an addition here and you want to remove common factor, like let that be the red flag that goes up in your head. Careful, careful, careful. And then all you have to do is come here and say, okay, now I have common factors. My final result would be x plus 2. Very common mistake, happens all the way through calculus. People get a little quick with it. They just kind of forget, what am I fluffing here? Okay. Equality of fractions. Remember, equality of fractions is that if you simplify them, they have to give you the same value. You can also build them up to show that they are the same value. So you have two different ways to do it. That are the two main ways. One is simplify both fractions. You can go to prime factored form, reduce the fractions with fluffing, and show that they're identical. You could rewrite them with the same least common denominator. Okay, perfect. Nothing wrong with that. Or you could even go to just any common denominator, because if you have common denominators, we're talking about the same type, and then you can compare the quantity. So if you were looking at and saying, okay, what about 3/7 and somebody else has 5/9, what you could do is say, I'm just going to multiply by that entire denominator and get 63 pieces by fluffing, because I fluffing love fractions. And that would give me 27/63. And over here, I would get 63 on the bottom because I'm going to fluff this one with a 7. And once I flop that with a 7, I get 35. And I can see this one is larger, which means this one over here has to be larger. If they were equal, then they'd be equal. So just remember, fluffing is your friend. There's nothing wrong with that. We'll see another way of demonstrating which one of these is bigger very quickly. And I think that's with the Kool-Aid property. And I think most of you are probably going to love the Kool-Aid property. So, all right, let's see here. So there we have equality of fractions. There is this theorem gives us a whole new way of doing this without having to go all the way through. Now, here's the idea. Remember those two that I just used, 3/7 and 5/9. And we're trying to figure out what symbol goes between them. Is it less than, equal to, or greater than? So what we did is we said, well, let's make this 7 times 9. And if we did, up here on top, we got 3 times 9. On the other side, we had 7 times 9. And up on top, we had 5 times 7. So we fluff with 7 on one side, we fluff with 9 on the other, and then we can compare. And I think, so what I want to get at here is, what are you actually comparing? You see, the denominators now are exactly the same because we fluffed them to be the same. So if they're the same, really, you almost don't care what those are because you know they're identical and you're really just comparing the products here. And that product turns out to be 9 times 3 and 7 times 5. But I need you to see where it comes from so that you don't just do this cross multiplying. Ugh, it's painful, but mostly because people use it inappropriately. So what you're really doing is you're checking if and only if AD equals BC. So if you want to know if two fractions are equal, yes, you can multiply here and multiply here, and this becomes 27 and this becomes 35, and they are not equal. So that is a pretty cool little theorem there. That is very helpful for equality. Next up is ordering. How do I know if one is bigger than the other? Now remember, you have to have the same whole object. So 1/3 of something might physically be larger than 1/2 of a different object. We need them to be the same. If we have the same, then we can compare how many. So if you take a look, if you have the same denominator, and again, really, really important, this property, this definition is for like denominators. So if they have the same denominator, you really can just look at the numerators because we're just counting how many. So it could have been jackets, it could have been peanut butter cookies, it could be anything. But we're looking at these with kind of some fractional pieces, right? So this is really important because that means it's very easy to tell which number is larger if you have 13/27 and somebody else has 14/27. You can tell, hey, we have the same object, 27, and you have 14, I have 13. Got it. You have more. That's how you can do it quickly if they have the same denominator. The issue comes up when they don't have the same denominator, right? So if they don't have the same denominator, guess what? We have our new best friend. Oh man, I fluffing love fractions. So if you had 4/5 and 11/12, and over here we had 11/12, right? I'd look and I'd say, hey, those denominators are not the same, but I could fluff them. And so I'll fluff this one with a 5. I'll fluff this one with a 12. And now I can compare because now the denominators, I could multiply that out and get 60 if I need to, but really it doesn't matter. It's going to be the same. I can tell these are going to be the same. Now I just look at the numerators. Up here, 5 times 11, that's 55. And 4 times 12, that's 48. Well, 55 pieces is more than 48. So I would say this one is larger. Okay? And that is what you're doing with this theorem at the bottom. What if they don't have the same denominator? Then even though it looks, they say A over B is greater than C over D. And it says if and only if, so this is a two-way street, if and only if AD is greater than BC. But I want you to see this piece. They are actually fluffing. They are actually fluffing. They're just not writing it down. Because once again, you have the same denominators, it goes back to that property that was at the top of the page that said if you have the same denominators, just compare the numerators. So that's really all they're doing here is fluffing fundamental law of fractions and then comparing. So pretty quick, pretty quick. Yeah. So there you go. Kind of a quick way to see when one fraction is bigger than another. And then this one is kind of fun. The denseness property. We have not had this before. This is a brand new property and it is amazing. We did not have it for integers. So for integers, we'd say, okay, well, how many integers are there between 1 and 5? And we could go find that, right? We'd be looking, how many integers are there? Well, there's 2, 3, and 4. Okay, there's 3 integers between them. And then maybe somebody says, oh yeah, well, how many are between 2 and 3? How many integers? And you'd have to say, there are no integers between 2 and 3. So that's it. That's the end of it. So the integers are not densely packed together. See, there's gaps, there's space between them. But rational numbers, between any two rational numbers, you can find another rational number. Okay, so if you had a rational number of 1/2 and I had the rational number of 2/3, we can look and say, are these the same? And we could use our quick little check, which would be 3 times 1 and 2 times 2. And I would say 4 and 3. These are not the same. Okay, they're not the same. You could also say the GCDs are both 1 and they don't look exactly the same, but there's many ways to do it. So now I'm going to fluff both of these things up to be some kind of common multiple. Okay, watch this. So if I flop this one with a 3 and I flop this one with a 2, then I get 3/6, and over here I get 4/6. And I'm like, great. I can clearly see now that obviously this one is bigger, but there's no fractions that I can spot quickly between them. So fluff it. I'm going to multiply by 2 and watch what happens. This becomes 6 over 12. That becomes 8 over 12. And guess what's sitting right in the middle? I know. There is a fraction. 7 over 12 is right between them. I know. I know. As a matter of fact, because of the way I did this, it's actually the midpoint between them, if you will. Let's try another one. We could go again, or we could go back and we could say, instead of flopping by 2 over 2, what if I had 3 over 6 and 4 over 6, right? And I got this one on the left, and I did by 3. I'll do 3 over 3. And this one go by 3 over 3. Okay, so now I have 9 over 18, and this one is 12 over 18. Guess what? 10 and 11 are right in there. So now I have fractions. I just found 2 fractions between them. As a matter of fact, if I count the one up here, I have 3 fractions between them. But if you use the property I showed down here, you can actually create an arithmetic sequence, which is pretty cool, right? An arithmetic sequence of fractions. Yeah, and again, these aren't simplified fractions. 10 over 18 would simplify. So would 9 over 18. So would 12 over 18. But again, it's just showing you how you can do it. So here's the property. Given any 2 different rational numbers, and it has to be different, there is another rational number between them, guaranteed every time. Whew. So there you go. Fluff it up. Oop, doop, 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 never stop. Oh, I should say. So really, if you think about it, if I use the number 2, when I had those 2 numbers, what do we have? Like a 3 over 6 and 4 over 6, and I use the number 2 to floff with, I got 1 number between them. When I use the number 3, I got 2 numbers between them. So it helps you to kind of see maybe there's a nice pattern there. Think back to chapter 1, where if I floffed with 5, maybe I could use this to get 4 fractions between them, but let's check. 15 out of 30. This is 20 out of 30. And then the fractions that I could get between would be 16, 17, 18, and 19. All of those out of 30. So I just found 4 fractions between them, and it wasn't that hard. You can find as many as you'd like to find. And that is kind of a quick way to do it. There is another way to do it if you want to find a fraction in between 2 fractions. This theorem, I call this theorem the Kool-Aid theorem. Now, depending on how you were raised, you may or may not have had something called Kool-Aid, where it came in a little packet, it's all flavor, and you had to add your own sugar. I remember that growing up. And so I used to love it when I could make Kool-Aid, because I would always put in like a little bit of extra sugar because I was like, ooh, it tastes good when it's a little bit sweeter. But every time that my mom came in and tasted it, then she would say, whoa, oh, it's too sweet, right? And then she'd go change it. So what I want you to do is I want you to think about this. Let's say that my mom decides to make some Kool-Aid, and she puts in 1 cup of sugar and 4 cups of water. Okay, that's great. You're probably even looking at that going, that's pretty sweet. But I really like it a little sweeter than that. So when I made mine, I put in 2 cups of sugar and 3 cups of water. That's right. I put in more sugar and less water. Very sweet. To this day, it probably would be like, ooh, that's way too sweet. But when I was a kid, it probably tasted amazing. Now, I want you to think about this. Sitting on the counter, there's like 2 different jugs, right? Of Kool-Aid. Like I got mom's over here and mine. So now what if I dumped all of those together? Okay, so mine over here is very sweet. Mom's over there is pretty bland, right? Well, what happens if you take something that's sweet and you mix it with something that is not as sweet, right? The sweetness factor goes down. So if I start mixing some of mom's in with mine, my sweetness is going to be closer to mom's. But if you mix it with mine, it's going to be sweeter than what she had to begin with. So both of them are kind of moving in one direction towards kind of this new type of Kool-Aid. And so if you just dumped all of these together, you'd actually end up with 3 cups of sugar and 7 cups of water. And what it turns out was great is if you think of these as fractions, you have created an order. 2/3, mine was sweeter than mom's. Mom's is over here. So yeah, 2/3 is sweeter than mom's. But if I dumped all of them together, I would end up with a fraction that is between them. And that's what this theorem says. Do not think for a second that I'm telling you that you add fractions and get 3/7. That is not what I'm telling you. What I'm saying is if you're trying to find a fraction between two numbers, you could do it by adding numerators and denominators separately and creating a fraction. I guarantee you it's going to be between them. Okay, so let me give an example, the one we just had, right? What was it? One half and 2/3, something like that, right? 1/2, 2/3. I went through the process to get a common denominator and then flopped it up to find things that are equivalent. But you could, if you wanted to, just add the numerators and add the denominators. So 1 plus 2 is 3, 3 plus 2 is 5, and 3/5 is between them. I guarantee it. Okay. Now, if you want to see why it's between them, go ahead and get a common denominator for all of these. So 2 and 3, the LCM of 2, 3, and 5 would be 30. So this one needs 15. The one in the middle needs 6, and the one on the side here needs 10. So if I flop these all, I end up with 15 out of 30. Over here, I get 20 out of 30, and this number in the middle is 18 out of 30. And yeah, definitely between them. Not dead center, though. It's not dead center. Like the other one that made an arithmetic sequence, that's great, but this is not arithmetic because this one goes up 3 and then the next goes up 2. So it's not creating arithmetic. So let me put that up here. This is not arithmetic. You're not hitting something that's dead center. You're hitting something that's between. And the reason you're not going to hit dead center every time is it depends on how much sweetness everybody else had. Okay, so what if my mom made hers like super bland and we poured them together, right? Well, then it's going to suck my sweetness right down almost nothing, right? There goes my Kool-Aid. But if she made a very small batch and then kind of put hers with mine, then we're okay. Then my sweetness part, I have more of my sweet part. It's going to just, it's not going to change it that much. It's only going to change it a little bit. So it's something to be aware of as you do use this really cool theorem, this Kool-Aid theorem. And why do I say that it's so cool? I want to jump back and show you because there was a piece, maybe it was over here. Maybe it was my example, because I was looking at ordering rational numbers. Maybe I'll just do maybe let's go back to the one that I had, which is like the 1/2 and 1/3. Let me share a new screen real quick. Okay, so the 1/2 and the 2/3, right? So if you happen to see, you can find out which one of these is bigger very quickly because you know this number is less than 1 because it's a half, right? So it's less than 1. And notice over here, this added 1 to the top and it added 1 to the bottom. So that means it's like using the Kool-Aid theorem, but comparing it to 1/1. So if I added the tops and the bottoms, right? So 2 and 1 added together would be 3. And up here on top, I had 1 plus 1 added together gives me 2. I guarantee you it's between them. And that also means that 2/3 is bigger than 1/2. So let's see here. What else did I have? I had 3/7, I think. Maybe 4. I'll do 4/7 because I'll do something just a little bit bigger than 1/2. So 4/7 is a little bit bigger than 1/2. And 5/9, that's a little bit bigger than 1/2. So now how do I decide which one is bigger overall? Well, take a look at the numerators. See, it went up 1. The denominators went up 2. So it's like comparing this to the fraction 1/2, right? Because I took 4 plus 1, I got 5. 7 plus 2, I got 9. So now I know that the fraction 5/9 is in the middle. It's between these two. And then all you have to do is say, well, which one of these fractions is bigger? So I have 4/7, which is bigger than 1/2, and this is 1/2. So that means I can tell which one of these is bigger. So I can do that pretty quickly as you go forward. What else? Let's see here. If I had a 7/8 and you had 6/7, right? Then you could look and say, okay, well, from 6 to 7, that adds 1. From 7 to 8, that adds 1. Okay, so I'm actually comparing this to the number 1/1. And I know 7/8 is between them, and I know 1/1 is bigger than 6/7, which means I can tell you that 7/8 is bigger than 6/7. So you can use this anytime. But a few good, really good pieces about fractions to know is that if you have 3/10 and 3/7, that 3/7 is going to be bigger. We should be able to get to that stage because this says there's more pieces. I've broken the whole object up into more pieces. There's more pieces, but I have the same number of pieces, 3. So again, if you have less pieces, the fraction's going to go up. So this is a kind of a big piece as the denominator goes up, right? So if you go up from 3/7 to 3/10, then the value or the size of the number goes down. Okay? And that's if you keep the numerator the same. Okay. But if you don't, if you keep the denominator the same, well, that one's even easier, right? 3/5 to 3/7. I did it. Or 3/5 to 4/5. I need the denominator to stay the same. If the denominator stays the same, you really just look at the numerators, and that one's really quick. So just be aware, if the numerators are staying the same, you really want to look at that denominator. If the denominator goes up, the size goes down. If the denominator goes down, the size goes up. Okay. So that is a really helpful one as well. And that, I think, is why when you start looking at it, you say something like 7/8, and you're like, oh, okay. Well, that means I'm pretty close to the number 1, which would be 8/8. Okay, you're off by 1/8. And if you said, well, what about 11/12? That's also very close to 1, which would be 12/12. You're off by 1/12. Well, look at these two. 1/8 and 1/12. 1/12 is actually smaller because the denominator is larger, which means 11/12 is closer to 1. So you could say 7/8 and 11/12, and you'd be able to say, got it. You could also use that other technique I showed where you just kind of say, wait a minute, this goes up 4 and that went up 4. 4/4 is 1. So I'm comparing this to 4/4, and obviously 1 is bigger than 7/8. So you can have that beautiful ordering coming in anytime you want. Very, very cool stuff. Hopefully this clicks for you. Again, we're just learning about these. We're not adding them together. Even though it looked like I was adding, I wasn't. I'm just combining numerators and denominators to get a fraction between them very quickly. Um, And you know what I should say? I should say this too before we go. I should say this. All right, so here's the idea. If you need to find four fractions between two numbers, you can do the find a common denominator, multiply by 5 to flop them up, and you're guaranteed to find them. But you could also do, let's say I had 1/2 and 2/3. If I need to find four fractions between them and I want to be quick, I could just add numerators and denominators like we just did. There's 3/5. But notice by the density property, I could repeat the same thing with these two fractions and get 4/7, adding tops and bottoms. I could repeat that again to get in between. That's 7/12. I could repeat it for the 1/2 and the 4/7. That becomes 5/9. All of these are between. I just found four fractions very, very quickly, and I could have gone to the other side and done 5/8. That is also over here. I could do it again and get 8/13, right? So you have a lot of options as you go forward. You could do it again between these two and get 13/21. And maybe some of you are like, so you could do this anytime you want. Yep. Come over here. 5 plus 4 is 9. 9 plus 7 is 16. Yep, that one's between them. So you could find as many fractions as you want quickly. That doesn't mean they'll form a beautiful sequence, right? 1, 2, 3, 4, 5, 6, 7, 8. I just found 8 terms between 1/2 and 1/3. I just found 8 fractions. But if I wanted 8 fractions to form an arithmetic sequence, then I'd have to say that I really want 1/2 to be over here, and I want to go 1, 2, 3, 4, 5, 6, 7, 8, 9 steps, plus 9 steps. That has to get me to 2/3. And if I want them to be equally spaced, I have to do something like creating an arithmetic sequence. And that would require us to come over and do a little bit of algebra. We have not gotten to this stage yet. I'm just letting you know, if you want an arithmetic sequence, we would have to find the difference between these two and then divide by 9. That would tell you the common difference, and that would tell you what you would add to get an arithmetic sequence with as many terms as you want. In this case, it would be 8. But this also demonstrates one of the sequences that we saw earlier in the course. So there was this beautiful sequence that you might remember that went 1, 1, 2, 3, 5, 8, 13, 21, and it came from adding two numbers to get the next. So 1 plus 1 gave us 2. 1 plus 2 gave us 3. 2 plus 3 gave us 5. So you add the two numbers, you get the next number. What I want you to see is if this was on a number line, 1/2 would be here, 2/3 would be here. And I'm choosing, basically picking fractions in a row. And also over here would be 1/1 if you want to go that direction. So 1/1, that gets me with 1/2. I add the tops and bottoms, I get 2/3. I add the next ones, I get 3/5. Then if I add those, I get 5/8. Add the next two, I get 8/13. Add those two, I get 13/21. Basically, I'm creating fractions in a row that keep getting closer and closer to a value on the number line. And so I am going to open up Desmos to demonstrate this because I think it's super cool. So Desmos, if I was looking at it, I could write, I'll do 1/2, 0. Okay. And so there's my point. And I'm going to zoom in on this because I want to really see this. Here we go. There we go. Okay, maybe I just need to change my settings real quick. Let's change the x-axis from -1 up to 1.2. Okay, so there we go. Okay. So if I start with, okay, so I start with the number 1, which is 1/1, the Fibonacci sequence, 1, 1. The next would be, so 1, 1. The next would be 1, 2, so it'd be 1/2, then it's here. Then I go to the next one, which would be 2/3, comma 0, right? 0.666. The next one would be 3/5. And so what I want you to see is we're kind of bouncing back and forth, but we do seem like we're getting closer and closer to something. Let's try the next one. It'd be 5/8. And then the next one would be 8/13. And so you can see is I am getting closer and closer. Let me zoom in. Okay, so those numbers now, there they are. Okay, 8 and 13. Hey, you know what? I'll do 13/21 because that's the next number. Okay. So you notice it's getting closer and closer to kind of a fixed position. 21 over, what's the next one? 34. Okay, so again, it's really getting close. It was bouncing back, it's bouncing, but it seems to be kind of locking in and honing in on a particular number. Let's go in even closer. So there we go. So what you can see is there's 3/5. There's 5/8. Here's 8/13. 13/21. So it's a little too high. This one's a little too low. And if I keep going, this would be 34/55. And you can see I'm getting closer and closer to a particular number. You can even keep zooming in. Next one would be 55/89. And so again, we get closer and closer to this number. In math, when we have something like this, and it actually shows we get closer and closer every single time, we have what's known as a limit. And this is actually approaching a very specific number. The ratio in the Fibonacci sequence is getting closer and closer to what is known as the golden ratio, in this case, the reciprocal of the golden ratio, which is 1.618. And if you look at the reciprocal of that, you get 0.6. Let's see here. Does it give me a decimal piece on Wikipedia? I believe it does. 1.618. And the other number ratio is 0.618033. And we are getting dang close to that. 0.61833. So I think the next number is 144. So I'll do one more here. 89/144, comma 0. And what we can see is if I get into that purple number here, that's 0.618. So I'm about a third of the way up to that next number. So 0.061833. And again, it's just rounding as we go. So this is a really cool feature of math that I personally enjoy, is being able to see kind of things that appear to come out of almost nowhere. It's like, what? How did that happen? How did we get to that value? So that's how you can do it with those fractional pieces. And it links back to the Kool-Aid property of adding numerators and denominators, and you end up at this thing that is called the golden ratio. So very cool. Hopefully you enjoyed that. Enjoy the rest of your day. Off you go.